Although what I'm going to do to save time is I'm going to do most of the sample calculations in the homework sessions. So we'll do a bunch. At the moment. What I'll do is I'll just give kind of an overview of the calculations, and then we'll look at specific calculations in the homework. This week, though, you know, we have the. Did I say about the rough draft for the reports? Have I talked about that? Okay. You still want to think about the reports, you know, as well. If you want to turn in a rough draft and show it to me, that's fine. We'll see if it's in the right direction or not. At least make sure you know, identify the acid and then start thinking about how you analyze the data. How you analyze the data would be like, you know, when you look at the curves, we have the titration curve, we have the first derivative curve, we have the second derivative curve, Grant's plot. You know, they all give the same equivalence point. You know. If not, what did you do? Did you average them? You know, these types of things we talk about in the discussion section. Maybe some of them weren't so good. You know, the plots were really hard to analyze, a lot of noise in there, making it difficult. Okay, once you get that equivalence point and calculate the molar mass, you know, was the molar mass in agreement? You know, how did the pKa agree or pKa's agree? You know, this type of stuff. We go through and then go through the steps involved in identifying the, you know, the steps that you use in identifying your. All right, so today we're going to look at some titrations and just general titration calculations here. Now, before we do that, let's talk about some of the things here, the jargon involved in titrations. Equivalence point. You know what the equivalence point is?
Isn't that where basically where the reactions like balance?
Yeah, right. You have like equal amounts of acid and base to react. Stoichiometrically equal amounts. This equivalence point. That's different than the end point. What's the end point of a titration? Oftentimes you can't see, you know, where you have the stoichiometric balance. And so we need something to tell us when we've hit that. And the something is the endpoint. The endpoint is when an indicator changes. For example, an indicator changes color, phenolphthalein, or something else changes. So ideally, an equivalence point and the endpoint should be the same thing, but often they're not. So what kind of error does that lead to? And so let's take a look at indicators in more depth here. So I'm going to jump to indicators here. An indicator is just a weak acid and a weak base, HIN and IN minus, and the colors have to be different. So HIN is going to have the acid color, and that's going to be in equilibrium with IN minus. IN minus, its conjugate base will have the base color. If the two colors are different, then we can use it as an indicator. Here. Basically, when we look at this equilibrium looks like the buffer equilibrium, you know, the weak acid and its conjugate base. And in fact, we can describe it using the Henderson-Ocelot equation. That is, the pH is going to be equal to the pKa plus the log of the base, which is going to be IN minus, over the acid, HIN. And so what's going to happen is the pH is going to change the ratio here of base to acid. Or, another way of thinking about it, like they're doing here, is Le Chatelier's principle. We could shift this equilibrium one way or the other by increasing or decreasing the hydronium. By changing the pH is going to shift this one way or the other. Those are two ways of doing this. And so let's look at phenolphthalein, for example. If this were phenolphthalein, then the acid color would be colorless. And the base color would be red or pink, dark pink, let's say, or red. And so what we're going to have is this. The color is going to depend on how much of each of these components we have. And so what we're going to do is we're going to look at the base to acid ratio. And if we have very little base and lots of acid, let's say a 1 to 10 ratio, so 1 part of base, 10 parts of acid, then what we're going to see is this is going to look for the most part colorless. In fact, if you go to 1 to 100, then it's going to be even more colorless. 1 to 1,000, the acid dominates. Acid dominates. Okay, on the other side, let's go to 10 parts of base to 1 part of acid. Then over here, the base color dominates. Base dominates the color, and it's going to look, red. And it's going to be even more a deeper red at 100 to 1, all the way to 1,000 to 1, etc. We can go the other way here. But what if we had a 1 to 1 ratio? If I had a 1 to 1 ratio, then which color dominates? Well, neither. What we're going to get is we're going to get a mix. And so at a 1 to 1 ratio, what we're going to see is a mix. The mixed color here is going to be light pink or light red, very light red. In fact, from 1 to 10, in 10 to 1, we're going to see a light pink color in this range here. Now, what pH does that light pink color come in? The pH that the light pink color comes in is this. If I had a 1 to 1 ratio here, then that would be the log of 1. The log of 1 is 0, and that means the pH is equal to pKa. So if I look at the pH here, the pH will be equal to the pKa. Yeah. If I go to a 1 to 10 ratio, then the pH is equal to the pKa minus 1, because log of 1 over 10 is minus 1. And then if I go up here, then it would be the pKa plus 1. So in this range here, pKa plus or minus 1, what we have is we have a mixed or intermediate color. And so for phenolphthalein, it would be light pink in this range. Light pink. So what is the pKa of phenolphthalein? The pKa of phenolphthalein is around 9. And so for phenolphthalein, therefore, we're going to see a light pink color. from 8 to about 10. Below, this is pH, 8 to 10. Below pH 8, it's going to be colorless. And above pH 10, it's going to be red. Now, is that going to lead to an error? You know, because our equivalence point, does it come in at a pH of about 8? So let's take a look here. So this is showing different indicators here, but one of the indicators is phenolphthalein. And so phenolphthalein, that pH is below 8, it's going to be colorless. When we hit 8, it starts to turn light pink. And that light pink color will continue to about pH 10. Above pH 10, it stays a dark pink or red color. And so it just continues red. They didn't draw the whole thing here. And so the indicator, this would be the end point. However, the equivalence point for this particular titration is here, pH 7. This is the titration of strong acid HCl with a strong base sodium hydroxide. The salt that forms is sodium chloride and water. And so that should be pH 7.
Just to clarify, so the end point is like the equivalence point of an indicator?
Yeah. The end point is the where the indicator changes color. So the end point of this titration will be here. What that means is we've overshot it. We've overshot the equivalence point. And we should have stopped at pH 7, but we overshot it and went up to about pH 8 or 9. Here is when we can start to detect that light pink color. And so that means we overshot it by about this much. That's pretty, that's pretty big error in terms of pH. Take a look at the error. In terms of pH, it's a big error. However, in terms of milliliters of sodium hydroxide, is that a very big error? No. This is like way less than a drop, like a tenth of a drop or something. And so the error is negligible here. So phenolphthalein is perfectly fine, even though it changes color and past the equivalence point. If I used alizarin yellow has a much higher pKa. pKa is around 11, so it starts to change the intermediate color around pH 10. And so the acid color is yellow, the base color is blue, and so the intermediate color is going to be a green, light green. So once I start seeing that intermediate color, I'm already at this pH way up here. That's where it starts to change. So this is going to be yellow, starting to turn green, maybe it gets green about here. Then I'm way past the equivalence point. So alizarin yellow would lead to a big error here in terms of milliliters. How about methyl red? Methyl red stops the titration a little early because the endpoint would be here of the titration, but would that be a significant error? No. Same thing with bromethymol blue and thymol blue. Thymol blue would lead to a big error here. We'd stop way too early. However, it looks like bromethymol blue is the best. This is bromethymol blue. Bromethymol blue has a pKa around 7. And so that means we'll get this light green color around the right point. And so the equivalence point and the end point are very close to one another here. The problem is, why don't we use it? We don't use it because it's hard to detect, the shades. Like sometimes when people see green, other people see blue. And so it's just easier to detect if there's a color change, the appearance of color versus a different shade of green or different shade of yellow, green, whatever. It's really hard. sometimes to determine. All right, so it's indicators and equivalence point and endpoint. Let's look at some more indicators here. So this is the equation I had up earlier. It depends on the ratio. All right, so bromothiamyl blue, which is the one that's probably spot on here, has a pK of 7.1. And so that means we'll have a mixed or intermediate color. Yellow and blue would be green, mix of those two. And the green would start appearing at about 1 to 10 ratio, which would be 6.1, and persist all the way to about a 10 to 1 ratio, which would be plus 1 or 8.1. And then above 8.1, the base color dominates, which is blue, and below 6.1, the acid color dominates, which is yellow. So this is just showing the 1 to 10, 10 to 1, and the intermediate color in between those two. All right. So there are a table of indicators that we can see here. And you can kind of estimate what pKa is here. So for alizarin yellow, the yellow is the acid color, and the acid color is going to dominate at 1 to 10, 1 part base, 10 parts of acid, and below. And so alizarin yellow stays yellow all the way from down here to here. So if you have a yellow color, the pH can be anywhere below 10. And then we get an intermediate color, which is the combination of yellow and violet, and then above 12 it stays as violet. And so the pKa for alizarin yellow is around 11. Phenolphthalein has a pKa around 9.5. Phenolphthalein has a pKa around 9. Thiamyl blue. And so we have lots of different indicators. And what we look for is the intermediate color. So if we use an indicator such as phenol red, all pHs less than 6 are going to be this color. And all pHs above 8 are going to be this color. And so if we have this color is unique, so we can kind of narrow it down. It's about 7. So here. This would be a good indicator for something that has pH around 7. Anything with a pH less than 6, we can't tell the difference. So if we try to pinpoint the pH below 6, we're not going to be able to do it. Also above 8, we're not going to be able to pinpoint the pH. So, same thing with thiamyl blue. We're looking at the intermediate color, although these don't match this bar, so I'm going to skip that. Methyl violet. Methyl violet is good for determining a pH of around 1. 0 that was okay too. 0 is yellow, and we can't go too far below that. But anything above pH 2, we can't tell the difference. It's going to stay viable. So I think they didn't print the whole color bar because it didn't cost too much ink. All right, so that's the endpoint and the equivalence point. Let's look at some titration curves right now, and then look at the types of calculations that we do. So we'll talk about the calculations involved in these, and then we'll look at specific examples in the homework. Okay, the type of calculation we do depends on what type of titration we have. And so the first thing I do is I look, what kind of titration is it? If it's a strong acid and a strong base titration, if it's a strong acid, strong base titration, then there are 4 types of calculations to do. One is the initial pH. Initial pH is just the pKa, the strong acid. This is chapter 16. This Ka, pKa or Ka, strong acid. And then we have the equivalence point here. At the equivalence point, we have a neutral salt. The equivalence point, I'll just call it EQ point. And this is a neutral salt. So, for example, sodium chloride. Sodium ions don't hydrolyze water, nor does chloride. And so the only thing that's hydrolyzing is water itself. And so the pH is 7.00. But between the initial pH and the equivalence point, we have what's called an excess strong base. Excess strong base, we have step I, which is solution dilution. Solution dilution. And then we have the next step, which would be step 1, or I'll just call it 2 here, would be strongest acid plus strongest base. And then the final step would just be Ka for the strong acid, the remaining strong acid. Up here, we're going to have the excess strong base. So again, we do solution dilution. This one?
No. The one that says first I. So solution dilution.
Oh yeah, this is solution dilution. Step I.
Why is that voluntary flow excess strong base?
Good question. It's excess strong acid, sorry. Excess strong acid. Up here would be excess strong base. And we just do solution dilution. The next step would be the strongest acid plus base. And then last step would be just Kb. Kb in this case is just hydroxide. Ka for strong acid is just H3O plus. So we'll do some calculations of this. This is more like Chem 1A stoichiometry here, but we use ice tables for it. The next type of titration we're going to look at is a weak acid, strong base. Weak acid, strong base titration. We're going to have 4 types of calculations. Same, but calculations are going to be a little bit different. Here, one, we start off at a higher pH, it's a weak acid. Strong acids start off at a lower pH. Strong acids start off at a low pH, and then there's a big rise up here. the excess base region here. The rise here at the equivalence point is going to be a lot shorter because we're starting at a much higher pH. So this is it here. In this case, at the equivalence point, it's not pH 7. The reason it's not pH 7 at the equivalence point is because we make a basic salt. We don't make a neutral salt. And so, for example, acetic acid plus sodium hydroxide yields sodium acetate. Sodium acetate is a weak base, and therefore the pH is going to be greater than 7. So this will be a weak acid plus strong base. Then we look at the initial pH. Initial pH is just going to be Ka for weak acid. And then we go up a little bit, hit the equivalence point. So the equivalence point here, this is going to be a basic salt. And so what we do, the steps involved here are 1, solution dilution. 2, strongest acid plus strongest base. And then 3, Kb for the salt. And that should give us the pH. Between the initial pH and the equivalence point, we have the buffer region. This is excess weak acid. Some of that weak acid gets converted into its conjugate base. So this is excess weak acid plus its weak conjugate base, which is buffer solution. But the calculation starting from the beginning are solution dilution, then 2, strongest acid plus base, and then 3, the HH, Henderson-Hasselbalch equation. Take us there. So that's between this point here at the beginning and this point at the end. And then past the equivalence point, we have the excess strong acid. So if you want the pH for the excess strong, no, so do it again, strong base, excess strong base region. 1, we do solution dilution. 2, we take the strongest acid plus the strongest base. And then 3, we just do Kb for the excess strong base, which is just hydroxide. The weak base we ignore. We ignore it unless we're right here, right next to the equivalence point. When we're right next to the equivalence point, then Kw is more important. Okay, so that's weak acid. Let's look at a diprotic, weak diprotic acid plus a strong base. For a diprotic acid, it's weak. So again, we start off at a little bit higher pH. So what we see is 2 equivalence points. The first equivalence point changes in the acid range. The second equivalence point changes in the base range. So the pH is greater than 7. So here pH less than 7, pH greater than 7. Okay, so let's take a look at the diprotic acid. And the types of calculations that we're going to do. One is the initial pH. Initial pH, we're going to use Ka1, maybe Ka2, it depends on how big Ka2 is. But definitely not Kw. Kw is going to be a minor contributor. So the first equivalence point is in the acid range, the second equivalence point is in the base range. So here, diprotic acid, weak diprotic acid. When we hit the first equivalence point, we make amphoteric salt and water. When we hit the second equivalence point, we make a dibasic salt and water. So let's take a look at diprotic acid. This is triprotic. This doesn't seem to be working here. Let's take a generic acid. We're going to call it H2A. A for some anion. And so when we hit the first equivalence point, we have H2A plus sodium hydroxide. This is going to yield the salt, sodium hydrogen A plus water, salt and water. This is what we call an amphoteric salt. And so when we hit the equivalence point, we add the equivalent amounts of acid and base, and we generate this salt. It's called the amphoteric salt because HA minus can lose a proton to form hydronium and water. Hydronium and actually HA. No, not HA, E2 minus. But also HA minus can collide with water and pick up hydrogen. If it picks up hydrogen, it forms H2A and hydroxide. So it's amphoteric because it can go either way in this collision. For example, the first collision with water yields hydronium, the second collision with water yields hydroxide. Now I mentioned when we were talking about buffer solutions in the Henderson-Hasselbalch equation, I mentioned we could either use Ka or Kb because they describe the same equilibrium. If I look at this Ka, this is a Ka for HA minus, and I look at this Kb, this is a Kb for HA minus. Do they describe the same equilibrium? No. They don't. This describes the equilibrium between HA minus and A2 minus. This describes the equilibrium between HA minus and H2A. They're different. But they're related because, one generates hydrogen, the other generates hydroxide. And they're going to be connected by Kw. So Ka, Kb, and Kw have to be solved. Ka, Kb, and Kw have to be solved simultaneously. Uh-huh. Yeah. Simultaneously. Versus when we're looking at buffers, we have Ka and Kb, but they describe the same equilibrium, so we only have to do one or the other. In this case, we have to do both. Ka and Kb, not only that, we have to look at Kw, because that's in high hydronium hydroxide. So this becomes very difficult. But there are some things that simplify this simultaneous. One of the things that simplifies the simultaneous is the acid and the base are the same. So the acid and base are the same. What we can do is we can go through the math, and we can use some assumptions, plus assumptions. This is simultaneous. And we can come up with a very simple equation. What this simplifies to is that the pH is equal to the pKa for the amphoteric plus the pKa for the conjugate acid in the amphoteric divided by 2. And so actually, what's looking like a really, really difficult simultaneous system to solve can be simplified into a pretty simple equation. So it's not difficult to get. So it turns out that in the diprotic acid, the first equivalence point is pretty easy calculation.
So amphoteric salts have conjugated acids?
Yeah.
Do they have conjugate bases?
Yes.
Okay.
Yeah.
And that's why we have to solve the simultaneous. Okay.
Well, if it's just a conjugate, we wouldn't necessarily have to solve it simultaneous. But it's because the same species is both the acid and the base. Let me talk about something like this. Aside, if I was looking at HA and A minus, HA, this is the acid, but is it amphoteric? Can HA be amphoteric? Well, HA can be an acid, but it can't really be a base. Yeah. And A minus is just a base. However, these are conjugates. And so, well, do I have to solve this simultaneously? And so if I look at HA for, well, HA plus A minus yields, the same thing. So I take the strongest acid plus the strongest base, I don't get anywhere. So I go with the strongest acid and the next strongest base, HA and water. And this is going to yield H3O plus A minus. And so this would be my Ka. And then I look at the Kb for A minus. A minus plus H2O liquid, this is going to yield HA plus OH minus. This is my Kb. And so do I have to solve this simultaneously? Ka, Kb, and Kw? No, I don't have to solve this simultaneously because these describe the same equilibrium. The equilibrium between HA and A minus, and the equilibrium between A minus and HA. So they're the same. Whereas when I go back to the equations for the amphoteric, they aren't the same equilibrium. And that's because the acid and the base are the same species, not the conjugate species of one another. So when we have an amphoteric salt, the pH is pretty easy. How about the second equivalence point? In this case, the second equivalence point is not going to be an amphoteric. It's a dibasic base. And if we want the pH of a dibasic base, then we look at Kb1, maybe Kb2. Depends on how big Kb2 is. But most of the time it's just Kb1. Okay, once we're past this, then we're in the excess base region. So a couple of things. Solution dilution is necessary for the second equivalence point. We need to do solution dilution. So I should have had that here. Solution dilution. Actually, let me write that here. First step is solution dilution. The second step is strongest acid plus strongest base. And then we repeat. The third step. And then the fourth step would be Kb1, etc. We might do Kb2 or Kw. We might do Kw if we'll write off the equivalence point here. Okay. However, when we do an amphoteric, we don't have to do solution dilution.
What does that say after strongest acid, strongest base?
Repeat.
Oh, no. Repeat step one.
Yeah, repeat step two.
I mean, yeah. I call the solution dilution step I, and then I start step one.
All right, then I should have done the same thing. Speed it up earlier. This should be step I, and then this should be step one. Step two, step three. That should be consistent with the earlier. For amphoteric, as long as this is concentrated enough, as long as it is not too dilute, solution dilution is not required. In other words, this is similar to the Henderson-Hasselbalch. You know, with Henderson-Hasselbalch, we just need a ratio. If we dilute it, then the ratio stays the same, the pH shouldn't change.
Define not to dilute.
Define not to dilute is hard to define. It's hard to define because it depends on the, yeah. Here, since you asked that question, I got the same question this morning. And so let's talk about, it would be similar to this, except this is a different example. This is from Henderson Hasselbalch and the buffers. What is to dilute for this? And so the question was for number 25, part B. So we'll take a look at this problem here and I'll try to answer based on this one. So this will be another side calculation here. So if we look at 25B, let's first look at 25A. So a handbook lists various procedures for preparing buffer solutions. To obtain a pH equal to 9.00, the handbook says to mix 36.00 milliliters of 0.200 molar ammonia with 64.00 milliliters of 0.200 molar ammonium chloride. Show by calculation that the pH of the solution is 9.00. Okay, so in chapter 25, let's do A first. We usually start off with a solution dilution. So let's go ahead and do the solution dilution. It's going to be 36.00 milliliters of 0.200 molar ammonia. I might run out of battery. I forgot my charger today. So if it runs out, I talked about this in the morning post. 64.00 milliliters of 0.200 molar ammonium chloride. So when we combine these two solutions, I'm going to get a total of 100 milliliters. But I need to figure out what my new concentrations are. So step I, the solution dilution. So it's going to be ammonia is equal to the dilution factor. The dilution factor is initial over the final 36 to 100. So it's 36 to 100 dilution, 0.200 molar. So what does that give us?